Hello, my name is Professor Matthew Schmidt, and welcome to Genetics. In this section, we're going to talk about the application of sex-linked traits to human genetic analysis. We did this once before when we talked about the application of regular Mendelian traits, and we found out that since you can experiment freely with things like peas and fruit flies, but not with humans, that we often have to rely on a pedigree analysis, which is basically a family history, in order to try and figure out the way in which a particular allele is passed on. Now, when we did it the other time, we talked about just the difference between a dominant and a recessive. And if you remember the term, we talked about only autosomal dominance and recessive. Autosomal means non-sex linked, and remember we talked about the chromosomes being autosomes that are not the sex chromosomes. What we want to do now is sort of integrate the idea of sex linkage by finding out, okay, once we know something's recessive or dominant, can we further tell whether it's sex linked, that is, in most cases that means the gene is located on the X chromosome, or is it autosomal, in which it's not located on the X, it's located somewhere else. In the problem-solving section, you'll find some more challenging examples of these types of problems, and since this is sort of a theory session, we're going to look at problems, but we're going to try to understand ways of what's going on here, how can we use the information, etc. So I call this part pedigrees, tips, and tricks. They're not really tricks, but what I mean is there are certain little shortcuts, which also sounds bad, but if they're applied correctly, you can save yourself a lot of time in trying to figure out one of these pedigree analyses. They can look quite daunting. Some of them actually are daunting. But a lot of times, if you can look at it in the right way, you still have to do your detective work, but you may be able to save yourself quite a bit of time and mental anguish, I dare say. So let's get a couple of things down here. Generally speaking, if a trait is sex-linked, and remember, we're talking about X-linked traits, those in which the gene of interest is on the X chromosome. It's not written in stone, but in real life, this is generally true, that more males are affected than females are. The reason is because since males only have one X chromosome, they have no other possible allele to sort of shield the expression, especially if it's a recessive trait. It's not necessarily the case. In other words, pedigrees can be designed, if someone wants to trick you, where it is in fact sex-linked, but more males are not in fact affected than females. But if you see that, it's a good sort of starting point. And don't get me wrong, females certainly can be affected, so you can't rule that out. That's just sort of a tip. If you see all males affected and no females, you might want to think about sex linkage. We said this next one before, but we want to remember it again. If a trait is referred to as rare or extremely rare, what that's trying to get into your mind is that people coming into the pedigree from outside the family, marrying into the family, do not carry the allele of interest, whether it's dominant, recessive, sex-linked, or whatever, unless the data prove otherwise. So if you see in the data that you see someone coming in from outside the family and there's evidence that they do carry either a trait or an allele, then that's the way it is. Data is data. But if it's rare and you don't see that, you're allowed to make that assumption. And again, while it's not proof, crisscross inheritance, if you see it consistently happening, it is a characteristic of sex linkage. Okay, so what I'd like to do is take a look at an actual couple of pedigrees, and here's one where it tells you right off the bat this is an X-linked or sex-linked recessive, and it's hemophilia. There are a variety of types of hemophilia, but the most common one is a sex-linked recessive trait. So in this pedigree, remember the conventions we discussed: circles equal females, squares equal males. Shaded in individuals have the disease, in this case hemophilia. they're showing us one other thing in this pedigree that you may or may not be shown if you're given a problem, and that is they're telling us who's a carrier and who's not a carrier. Now, since we know that this is X-linked from the beginning, a male could never be a carrier, right? Because if you have the allele, you're showing the disease. If you don't, you're not. So that's one thing about sex linkage. For a recessive trait, a male could not be a carrier, but females can, and they're being shown, as you see in the legend up here, as they have a circle with a little circle inside that's purple. Usually you probably wouldn't be shown that information, but remember, in this type of a session, we're trying to understand what's going on in these pedigrees. You can apply them later in the problem-solving sessions. So basically, one thing you can do is, I told you this before, there's no absolute 100% rule about how to approach these pedigrees. You have to do some trial and error. You have to look around and sort of see what you see. So one thing that I would notice just right off the bat is that let's look at all the affected individuals. And by the way, I should have mentioned this is an actual pedigree of part of the royal family of Queen Victoria. There was hemophilia in that family, and these are actual, it's not the complete pedigree of everyone, but it's sort of pieces of interest. So this is real data. Notice that all of the people who actually have hemophilia, Leopold, Rupert, Alexis, and some other dude that we don't know his name, they're all males, right? So while it's not proof, this does go to the idea right off the bat. If you didn't know already, you might say, this has the characteristics. I don't see any females being affected. Only people who are affected are males. That sounds sex-linked to me. So you keep that in mind. We also want to say, if we were approaching this from the point of view of just what is this, is it dominant or recessive? Well, you can tell it's recessive right off the bat by the same principle we used before, right? Rupert's not the only one, but he's got the disease, and neither of his parents have the disease. We said that that's the hallmark of a recessive trait. So this is more about the sex-linked aspect, but I just want you to realize that it's definitely recessive. So then the question becomes, is it X-linked or is it autosomal? I know you know it's X-linked, but let's see how we can sort of prove that. Well, one way is, let's take a look, do what we did before and see if we can tell the genotypes of these individuals. Given that it's sex-linked, let's try that first, and then we'll try it if it was autosomal and see if that works or doesn't work. One thing is for sure. So the way we did it last time is we said, here's a hypothesis. Let's just make it easy. The hypothesis is that the hemophilia allele is sex or X-linked. So in that case, anyone who has it, right, Leopold, for example, has to be, arbitrarily, I'll just use H for hemophilia. He's got to be X little hy. We already established it's recessive, right? Now, what this means is, if Leopold had a daughter, remember, males always give their X chromosome to their daughter, and he did have one daughter, so here she is. We know she has to have at least that. Now, since she's a carrier, she also has to have one big H. It's lucky we can see she's a carrier here. Where did that big H come from? It came from her mom, Helene, who was coming from outside the family. So the implication is that she was homozygous, right? But regardless, we know that she gave one X with a big H to her daughter. That's what makes her a carrier, all right? So that's sort of consonant with the idea of sex linkage. Since there are no affected women, it's hard to really, ask ourselves, well, here's an affected woman. Let's see how the behavior is with her. But you can do one thing. If we start putting in genotypes here, Queen Victoria was a carrier, right? And we can sort of follow this down. Prince Albert, assumedly, was not. So here's all the kids they had in generation 2. Victoria, Alice, Edward, Alfred, Louise, Arthur, Beatrice. Helena is supposed to be a male, as it says here. I don't know about that, but we're going to have to take for granted that she's a male.